For a fixed bias circuit or collector to base bias circuit, the values of DC collector current and collector voltage are found to be dependent on the current gain, or beta. But the value of the current gain, beta, is temperature sensitive. So, there is a need to provide a DC bias circuit which is independent of the transistor current gain, or beta. The voltage divider bias, or potential divider bias, meets this condition. The name potential divider is derived from the fact that the resistors R sub 1 and R sub 2 form a potential divider across the VCC supply. The emitter resistor, R sub E, provides the DC stability. A voltage divider resistor scheme with R sub 1 and R sub 2 fixes V sub B. In this case, transistor is always forward biased. V sub B equals V sub BE equals 0.7 volts. Hence, I sub B is fixed by V sub B, so I sub C equals beta times I sub B. The emitter resistor and thermal stability. Electrons and holes are generated by thermal effects. So, these carriers increase with temperature. Hence, there is an increase in the leakage current. In biased transistor, the base to collector junction is always reverse biased. The collector current includes leakage current. If I sub C increases, so does the leakage current. Thus, the operating point shifts. Hence, the device heats up and leakage increases. Thus, I sub C increases and I sub E increases. This leads to thermal runaway, which can destroy the transistor. An emitter resistor fixes emitter voltage, V sub E, and emitter current, I sub E. If I sub C rises due to leakage current, so does I sub E and V sub E. But base to emitter voltage equals to the difference between the base voltage and the emitter voltage. Thus, if V sub E rises, V sub BE comes down. Hence, the base current I sub B reduces the collector current I sub C, and the operating point is maintained. An emitter resistor is used to enhance the thermal stability under DC bias.